So, we're going to talk today about nuclear radiation. So, what is nuclear radiation? Well, it's radiation, it's a reaction that's going to involve a change in the nucleus. That's where they get the term nuclear because it's dealing with the nucleus of the atom. And as we learned in our last set of notes, the nucleus contains neutrons and it also contains protons. So we're going to look at those different parts of our atom and the nucleus and see what changes about them. Um, the changes then are going to emit what we call radiation, and there's forms of radiation that you're exposed to on a daily basis. Radio waves, microwaves, light waves, all of those are fine. We don't have any problems with those. But when we get up into like UV rays, for example, they can cause problems. That's why you need to wear sunscreen because they can cause cancers. And it has to do with the fact that they make molecules do things that they shouldn't normally do. And then you move up into X-rays, and that's why they always put like a iron or a lead apron on you when they're doing X-rays. And then even more frequent than X-rays would be uh, this radiation, these gamma waves, gamma rays that are emitted. And then we also have a couple other things called alpha and beta particles, which we'll get into in our next video. So these nuclei become unstable and they're going to give off this radiation and try to get to be stable. So the nucleus kind of pushes apart due to the electromagnetic forces. So that's what you would expect to happen because we have like charges in the nucleus. Those protons are in there. And the protons would normally push each other apart, just like if you had two poles of a magnet that came together that were the same pole, it would push apart. But there's actually a force inside the nucleus called a strong nuclear force, which holds those positively charged particles together. And it overrides this tendency to push them apart that we're so used to hearing about. But here's the kicker. This strong force only works over very, very, very small distances. We're talking like the size of a nucleus, which is just so ridiculously small that we can't even really perceive that. And so those strong forces, as the nucleus gets bigger and bigger and bigger, as we move down the periodic table and we add more and more protons and neutrons in, this strong force, the distance becomes too great and it can't hold everything together. And so parts of the nucleus start coming off. And that would be like your protons and certain neutrons are coming out. And we'll learn about those things and what they're called in the next video that deals with alpha and beta particles. Those are the ones that we cover in this course. There's a couple other ones that we don't cover. But if you get into more advanced coursework, you will hear about those. Or sometimes people who take physics will also get into that because we're starting to dip into the physics pond here a little bit with some of our discussion of nuclear radiation. This is what I was talking about with the strong force. Again, normally we would expect our protons to be pushing one another apart. Instead, they actually hold together. And that strong force is what holds it together. So how do we determine if an atom is stable? Well, the stability is determined by the ratio of neutrons to protons. So if that ratio is about 1 to 1, then we're pretty stable. If, however, we get to be like 1.5 to 1, then the atom starts to become unstable. And it's going to continue to decay or lose some of those particles until it becomes stable. And it usually decays down to, like if we're talking about like uranium or plutonium or something like that, it'll usually decay down until it gets to about lead. And once it hits lead, then it's usually considered stable. So one of the things that we do when we get to this unit is we talk about half-lives. And this, for example, is an iodine 131. Half-life means that we're going to take a certain material, and over a certain amount of time, half of that material is going to change into another element. And we'll talk about how that happens and why that happens in the next video. But right now, you just have to take it as a given that if we started out here and we went down 50%, now that material isn't just lost to the universe, it is becoming something else. It's just not iodine 131 anymore. It's something different. Okay. So half of it is getting changed into something else. Then, if we wait the same amount of time, half of that material will change. And if we wait the same amount of time, half of that material will change. And that's called a half-life. So the half-life here would be 8 days because it takes 8 days for half of that material to change into something else. And then if we wait another 8 days, another 8 days, and every time we continue, we keep going down by half. So we have a few problems here that we're going to work through, and I'll show you how I do these. There are different ways of doing this, so you can certainly feel free to look it up on the internet, however you want to do it. I do need to see work for these, so you can do them the way I do them. You can do them more algebraically if you want to find another way to do it, but I need to see your thought process in getting your answer. So if you want credit for this section, you have to show me your work. All right. So we're starting out with 120 grams of radium, and we want to know how much will be left after 44 days. The kicker is that we need to know what the half-life of this radium is. So give me just 1 second to look that up, okay? So here is where I got that from. I think. Yeah, here it is, radium. So the half-life for radium is for this radium sample is 11 days. So that we needed that. Okay, so as long as we know that, we can continue with our problem. So if our half-life is 120 days and we're starting out with 11 days. We're starting out with 120 grams of this. If we go 11 days, so this time sequence here, we've gone 11 days now. Half of this will be left over. So half of 120 grams would be 60 grams. Okay. Now we're going to go for another 11 days. After another 11 days, so how many days total is that so far? So our running timeline here, so far we're at 22 days total. Okay. If we go another 11 days, we're now down to 30 grams. If we go another 11 days, again, if we're keeping a kind of a continual timeline, that's going to be 33 days. We're going to have 15 grams left. We keep having the amount every time. And if we go for another, so we get to 44 days, we're gone another 11 days, we're going to have half of that amount, which would be 7.5 grams. And so if you start with 120 grams of radium, how much in grams will be left after 44 days? Your answer will be 7.5 grams. And that would be your answer. Okay, so let's try another problem here. This one, we've got 80 grams of thorium, and we've gone 24 days. If by the end you're left with 40 grams of thorium, after another 24 days, you have 20 grams of thorium, and after another 24 days, there's only 10 grams of thorium. What's our half-life? Well, every time we've gone down by half. So half-life is the amount of time it takes for a sample to go down by half. So here, our answer would be 24 days. Let's try one more. Here, we're starting with 20 grams of thallium. We've got 20 minutes. After 20 minutes, we have 12.5 grams left. They want to know what the half-life is. So we're going to take this, we're going to start out with our starting amount, and we're going to keep dividing it down until we get to this amount. So I'm going to start at 200 grams. If I divide that in half, that's 100 grams. If I divide that in half again, that's 50 grams. If I divide that in half again, that's 25 grams. And if I divide that in half again, now I'm at 12.5 grams, which is where we needed to be. But that doesn't answer our question. They're asking us what our half-life is. Well, what they've told us here is this whole process here has taken 20 minutes to occur. So 20 minutes for this whole entire process has gone on for 20 minutes. So we need to take how many times we divided this and divide 20 by that. So how many half-lives do we go through? We went through 1, 2, 3, 4 half-lives. So if I take 20 minutes and I divide that by 4, that means that I've got 5 minutes for each of my half-lives, and that's my answer.